Hi everyone, this is Mrs. J, and today we are starting Unit 6, which is all about circles. So today we're going to talk about central angles and inscribed angles within a circle. But first, some extra vocabulary. So first, a chord is a segment whose both endpoints lie on a circle. So for example, if you look at the figure to the right, AB is a chord, and BD is a chord. So again, endpoint and endpoint are both on the circle. A central angle is an angle that's less than 180 degrees whose vertex lies at the center of a circle. So we can see a central angle right here, ACD. And one thing I do want to point out is that the measurement of your central angle is always equal to the measure of the arc that it makes. So that is one important thing to note. So if you know the measurement of this arc, then you can find the measurement of the central angle. And last, the inscribed angle. An inscribed angle is an angle whose vertex lies on the circle, like you can see right here, and whose sides contain chords. So ABD would be an inscribed angle. So you can see again, its vertex is on the circle instead of in the center. Okay, so now we're going to talk about the different types of arcs. So an arc is just a continuous portion of a circle consisting of 2 points and everything in between them. So here in this picture, we have a point A, a point B, and the measure and everything in between is that arc. So adjacent arcs are simply two arcs that are right next to each other, so they share a common point in the middle, like DE and EF. Those would be adjacent arcs. And intercepted arcs are arcs that consist from the endpoints of an inscribed angle. So here's an inscribed angle, and then this in red would be the intercepted arc. So more specific types of arcs. A minor arc is an arc whose points are on the interior of a corresponding central angle. And again, you'll see here the measure of a minor arc is equal to the measure of its central angle. So this it would be our minor arc, AB. And also note that we name it with just 2 letters. So for a minor arc, you only need 2 letters. So it will be an arc that is less than 180 degrees. Now, a major arc is an arc whose points are on the exterior side of the corresponding central angle, which is just a fancy way of saying it's an arc that's larger than 180 degrees. So, for example, that would be this arc. Now, I do want to point out for a major arc, you do need to use 3 points to name it. So notice it's A, D, B. And last, we have a semicircle, which is an arc that is exactly 180 degrees, so it's a half of a circle, and its endpoints will always be on a diameter. And you can tell, again, this is a diameter because it goes through the center, and both A and B are on your circle. Okay, so I want to talk about 2 different postulates and theorems that we're going to be using today. So the first is called the arc addition postulate. This is really a common sense postulate. It's very similar to the angle addition postulate or the segment addition postulate. All it really says is that a small arc plus a small arc equals a larger arc. So here, if you have arc AD and arc DB, it makes arc ADB. So it just combines the 2. Or we could look at the figure to the right and we could say, oh, arc DE plus EF would simply make arc DF. So again, it's more of a common sense postulate. And then the second one is called the Inscribed Angle theorem. So this is going to be an extremely useful theorem for us. It says that the measure of an inscribed angle is equal to half the measure of its intercepted arc. So again, here we have an inscribed angle. Here is the intercepted arc. So the angle is always exactly half the arc. Or if you're going backwards, the arc is always going to be double the angle. Okay, let's give these two examples a try together. So here our goal is to find all of the missing angles and arcs in the two figures shown. So when I look at this first circle, one thing that you might notice right off the bat is that AE, segment AE, is a diameter. So we know that because it goes through the center and both endpoints are on your circle. So we know that a diameter cuts your circle in half. So that means that this entire measurement right here should be 180 degrees. So it's half of a circle. So if I know that the entire measurement, let's set up a little equation. We know that arc ABE, ABE is 180 degrees. And we see that BE, arc BE, is 18 degrees. We know that we can find the measure of arc AB by doing 180 minus 18. So we get 162 degrees. So now that we know this measurement, let's kind of work our way backwards. Again, we knew that this entire arc ABE is 180 degrees. And you'll notice that it actually goes with an inscribed angle. So this arc, the full 180 degrees, goes with this angle. So remember, the inscribed angle is always going to be half the arc. So if the arc is 180 degrees, then this angle right here, angle ADE, should be 90 degrees. And then if we look a little bit closer, here you can see that we have a triangle. It's actually a right triangle. So if we know two of the angles, we should be able to find the third because they should all add up to 180. So that means this last angle right here should be 36 degrees. Okay, so now let's look at the inscribed angle that goes with arc BE. So here's arc BE, and then the angle that goes with it is right here. So remember, the angle is always exactly half of the arc. So if the arc is 18 degrees, this angle should be 9 degrees. And then we can go from this angle to arc ED. So again, if this angle is 54, let me color it in green. The arc that goes along with it should be exactly double that. So that means that ED should be 108 degrees. And then our last one, we could use angle AED, which is 36 degrees, and then we double it to get arc AD, so that should be 72 degrees. Okay, let's try the second example together. So again, one thing that you might notice is that we have a diameter. WZ is a diameter, which means that this entire half circle should be 180 degrees. So if the entire half circle is 180 and then we subtract out 106, that leaves us with 74 degrees for this arc. We can also use arc WZ to help us find the inscribed angle ZWY. So remember, the arc is always double the angle, or the angle is half the arc. So if the arc is 106 degrees, that means that this angle should be 53 degrees. Let's travel over to this part. So here we are given another inscribed angle, which is 9 degrees. So that means the arc that goes with it, arc WX, should be double the angle. So this should be 18 degrees. And again, we have another half circle on this side, which we know should add up to 180 degrees. So we simply subtract 18 degrees from 180, and we get 162 degrees for arc XZ. Okay, let's look at example 2 together. So here we're given that angle EDF, which is right here, it's an inscribed angle, is 15 degrees. And they're asking us to find the measure of angle ABE. So here's what we're trying to find. So you can see that ABE is an inscribed angle. So if we knew what this entire arc length is, then we could find the angle. However, we are missing this portion. Luckily, again, we were given that this angle was 15 degrees, which means that arc FE is double that. So this is 30 degrees. Therefore, we know that arc AE from here to here is simply 44 plus 30, so it's 74 degrees. And since we know the intercepted arc length, we just divide it by 2, and that will tell us the measure of the angle. So therefore, we know that the measure of angle ABE is 37 degrees. Okay, so the last thing you'll see here is what's called the inscribed angle of a diameter theorem. So this is actually something that we saw in a previous example. And it says that the endpoints of a diameter lie on an inscribed angle if and only if the inscribed angle is a right angle. So again, this is something that you don't need the theorem to tell you this, because again, we know that a diameter creates an angle that is 180 degrees, or it creates an arc that is 180 degrees. So if it has an inscribed angle, that angle will always be half of that arc measurement, which must be 90 degrees. So again, it's something that you could figure out without knowing the theorem, but it does have a name, so now you can use it in the future. All right, so that's all for today's video. Thank you so much for watching.